I get a link to our page, right? We have to be in the LMS by next week, so I can put every class out there stuff on me. Just make sure you're in the LMS. Some of you are seeing here, but you have to work. Right? So it means that you would have gotten the email. So what we'll do is we'll give you a link, please log in, we'll give you a password and username, and you'll see if that will help. But I think some of you are not getting the email. All right. As I was saying, we're going to take a look at electromagnetic induction. Here goes, this is the thought. We are going to take a magnetic field, right? We are going to take a magnetic field, right? A magnetic field, and we're going to take a conductor, and we're going to move the conductor in the magnetic field. And what is going to happen is going to induce electricity. That's okay? So whenever you have a magnetic field and you move a conductor in the magnetic field, remember there's a magnetic field here, right? When you move the conductor in the magnetic field, you are going to get a current in here. Okay? Those who ever use a generator, maybe for like pumping out something, you'll ever use a light and you have to wind up the light. Yeah? Right? Now, pumping. Okay, so you probably do that in November, right? So basically, a generator is something like it has a crank up. And by cranking it up, what you're doing is you're moving a conductor in the magnetic field. And what will happen is that mechanical energy that you are applying is being converted into electrical energy. That's okay? And the rule that we use is the Fleming's right-hand rule. Right? Same thing, same meaning. So you have the thumb, your first finger, and your middle finger. Right? Thumb is the force, right? It's the applied force. First finger, magnetic field. And your middle finger is what you're trying to find. It's called the induced current. All right, so before you write that, take this note. It was right already, but good. Take this small note. When it conductor, right online, take this small note first. When a conductor is moved through a magnetic field, is moved through a magnetic field. Is moved through a magnetic field. It continuously cuts. It continuously cuts. It continuously cuts the field lines. Full stop. This induces a current, put in brackets EMF, if you have voltage that EMF. Yeah, all of it. This induces a current in brackets EMF in the conductor. Full stop. The direction of this current is given by the direction of this current is given by Fleming's right-hand rule. Is given by Fleming's right-hand rule. Right, and then you can draw this and write this rule, and we'll do a few examples. Never pick jackets there. Anybody missing a jacket? Anybody missing a jacket? So one last week. Anybody writing here? Who's there now?
Yeah, but see,
Right, make a note. Make a note that we're trying to find this, right? So you'll know which finger you're trying to find. Okay, now wait. So in the left hand rule, we're trying to find the top. In the right hand rule, we're trying to find the middle finger. Yeah. All right, let's go. Example 1. Right? Just like what we did with the left hand rule, we're going to apply it with the right hand rule, right? So example 1. So remember, you must use the right hand rule. How you know when to use the right hand rule? Whenever you see a force being applied and they have to define current, right? So we are going to apply right hand rule, next right hand rule to find current direction, right? That's okay? So watch it here. Right hand rule, magnetic field is where? Magnetic field is north to south. So your first finger is where? North to south. You all okay with that? First finger, north to south. And the force is where? Down. So your first finger going that way and your thumb now have to go down. So I'm going to turn it like this. What direction the middle pointing in? Outward. Out is what? Dot left. Right? What's it again? Magnetic field. Remember, you have to do this based on what you draw in your book or on the whiteboard. Okay? So magnetic field north to south. So my first finger pointing north to south. But the fourth pointing where? Down, right? So my thumb has to go point downwards. So I turn everything. And then the middle finger pointing outwards. That's okay? Right? For those who knew, remember dot means what? Out, X is in. Right, number 2, people online only to answer, right? Nobody has to answer, right? You can work it out, don't answer. And when you want to hear online, well, see online, send a response. So online, tell me to put a dot for X. North to south, the force is up. Online, message dot for X. Good job, Ethan. To me alone, and not to everyone. Joshua dot. All right, you'll see that now. I'll just say it loud.
So somebody else.
Right, good chief, good. Good chief. I have 3 people so far. I'm waiting on the others. Narisa, okay. 4. Okay. Online, Serena, Anaya, Emily, okay. And I only got 5 online. 17 more. Online, need some more. All right, let's go. What's your guess? Dot or X? So can you repeat the question? Okay, yes, yeah, I'm doing it here. So we need to figure out if it's a dot or if it's an X, right? Going back again, right? What are doing wrong here? Wrong hand, right? Right hand rule. Okay? Right hand rule. Right hand rule. Must be a right hand. So, right, for those who knew, you start with the thumb, 90 degrees, stay your thumb, 90 degrees, stay your first finger, right? Force is where? Up. That's okay? So the force is upwards, right? Magnetic field is where? So this finger has to point towards me, right? So the middle finger is pointing out. Out is up. Out is up. Let's go again. Right, I'll pick somebody in here to come up on the board and do it. If you're new, more than likely I pick you. Yes, new. All right. Figure it out quick. Dot to X. That's a Rayo big shoot. That's a Rayo big. Yeah, come on, go. Oh, wait, yeah, there's some all you got. That's easy. That's not dot to X. Right, but you gotta show my how big a dot to the X. Yeah. How you get dot to the X? So your magnetic field is which one is magnetic field? Which one is magnetic? Which one is magnetic field, right? This one is what? Current, you're trying to find on this one here is what? Right. That's it. So put this finger towards the force.
Okay.
Force pointing in that way. How you gonna do that? So watch. Watch. So use my hand. So this finger going away. Right. So we make it point like that. Right. And the magnetic field as well. North to south. North to south. So what to do? So what direction the pointing in? No, this in or out. So what to put? Right? So you have to keep your finger like it's not aligned. Okay, watch. I aligned it there. Force, magnetic field, current going in. All right. But here this one. So watch it again, right? Magnetic field, north to south. So you magnetic field, north to south. So it's going down. The forces away from me. Magnetic field, force. So the current is pointing towards me. See that? So I'm going to give you one next step. Right? Behind Tudor. Joanna. Ready? Last one. Last one before we change it up. And I know you can figure it out, work it out, right? Work it out, tell me what you got.
I know. Yeah. Oh. I need that. No, you didn't. Well, I get my grade, guys. I got. She can't grab it. Yes, I did go.
Right? Let's see what you got. What you got? Show me the rule first. Very good. Oh, block it online. Right, X. Right, so magnetic field, north to south, current going, sorry, force going towards me, magnetic field north to south, so therefore answered in. That's okay? Next heading. Lenz's law and Faraday's law. Faraday and Lenz's law. I'll spell it for you up here. Yes, that's the same guy. Correct? Faraday's and Lenz's law, right? So these two guys were the two guys who kind of explain why it is we get in a current, right? And I just want to show you a simulation, and from the simulation, I'll be able to explain what's happening, right? Go ahead, see. All right, so I just going to show you a small simulation here.
Yeah. So the discussion. Pretty.
Let's try this one, right?
When you open the screenshot, but if you have the screen.
This one on the. Only one on the. Alright, online, you all see it or no? Online, you all seen anything? Right, you did I show you the bar magnets already?
What?
Did I show you the bar magnets simulation?
Yeah, that's so shut down.
Right, so watch here. Yeah. Right, so look at that there. What do we have there? You see the magnet? Magnet will have a magnetic field, right? And you all see the coils? Well, it's not a Rubin coils. Right? Now, what did we say earlier? We said that if we move based on the left hand right hand rule, we said that if we move, right, a conductor in a magnetic field will get current. Are you okay with that? So if I look here, around the magnet there's a magnetic field, right? I'll show you it for a little while, it'll be confusing, right? Right? But that's the magnetic field. What you call those small things again? What you call the small things again? The little triangles, compass, right? And we use that to show its direction. Okay? So here's what we're going to do. We are going to move this magnet in and out of here. And what will happen is as I move the magnet in and out of the coils will cut the field line. So watch it here, right? I'm going to show you the field line. Watch it there.
Yeah.
So I'm moving it in and I'm moving it out. But what you reckon is happening up there? It lighting up. So it means that by me moving it in and out, I am getting what? Electricity. So the magnetic field being cut here producing current. That's okay? Let me see if I can show you the electrons. So watch. Right now there are electrons in the conductor, right? Right? There are electrons. But only when I move it, recognize the electrons moving. You see that? Yeah. So what you observing there is a simple generator. All right. Watch this here too, right? Wait, no. Watch this one. I just taking off the line. What would happen when I turn on the water? Any guess? What would happen when I turn on the water? Right? It was spin, right? Right? The magnet will start to rotate. What will that do? Right? Yes, it will produce electricity because the field lines from around the magnet will be cut by the conductor. The field lines moving, so it's going to produce a current. Right? Watch it here. One minute. And water. See that? So that's a simple generator. Watch this here. So the magnetic field lines, as it moving, the magnetic field line cutting the conductor, and the conductor, the electrons in the conductor getting excited, and they're moving, and they start to move. Once the electrons move the shield, what do we get? Huh? What's happened? What's happening when electrons move? What do we get? Well, technically, you know, right? But when electrons move, it gets current, right? Right? So the magnet, basically magnetic field causing the electrons to move. And when the electrons move, we get electricity. Right? And we can see it there. Everybody okay with that? That's a simple generator. Your homework is to go and make it. Right? Have a long weekend next week, or you can make that. No, ma'am. Everybody okay with that? Right. So we have two laws to learn here. Lenz's law and Faraday's law. I can show you Faraday's, right? Tell me why it is no current here. Oh, sorry. Why it is no current here? Let's take off this thing. Right. Why it is no current? So the water giving it. Right. What you will recognize there is the reason that there is no current is because the magnetic field lines not really moving, right? So the magnetic field lines are not cutting the conductor. But watch what will happen. Watch what will happen. We'll put a little bit. Right. See how it is? You get any electricity, but the ball not bright. But watch this here. If it moves faster, it becomes bright in pulses. Right? So here what Faraday said. Faraday said that the faster the field lines cut the conductor, the more current you'll get. You're seeing that? So the faster the field lines, because the field lines is around the magnet, right? Faster the magnet moves, the faster the field lines will cut the conductor. Conductor is the coils. So okay with that? Right. Lens now, I don't know if you want to see lens. Right? You might be kind of small. The lens's law tells you the direction the electrons will move in. Watch it closely. You'll see the electrons going one direction, then change it. You'll see that? So lens is the guy who will explain that. Okay with that? So you might recognize the current not moving in the same direction all the time. So go in one direction, then it changes. You're seeing that? So Faraday said the faster the field line cut, bigger the current. Lenz said the direction always opposes motion. I'll explain now another one. Okay with that? So what you're observing there is a simple generator. All right? Of course, The generator you have to draw is this one here. Right, if you want to see the simulation, you can always Google PHET or Java Lab, right? Right, this is the one that we are going to explain this now. All right, none. That's not generator.
Oh, that is.
I did not see that.
I really not.
See, like, big up.
Some like some like a real. Right, watch it here. Right, you all might recognize this. Does it look similar to a motor? Yeah, it's similar to a motor, except you all recognize that they are not batteries. So there is no current being supplied. A motor has what? Current being supplied because it's electrical, giving you mechanical, right? But a generator is mechanical, giving you electrical. You're seeing that? So it's very similar, but there is no supply. By moving the conductor, you will get the electrical energy. Anybody seeing a next difference? Huh? It don't have split rings, it has slip ring. Watch it there. It's a whole ring, right? You're seeing that? It's a whole ring. The one that we did last week was a half. So the motor has split ring. Generator has slip ring. Okay? Motor, generator. All right? So we'll do that in a little while. All right, nice. Let's go back to the little notes there. Right, so you can always look at these little simulations to understand what's going on. Right? So Faraday's law, take this note. Faraday's law states that that's just what I was showing you there. Faraday's law states that the rate at which the magnetic field lines, the rate at which the magnetic field lines the rate at which the magnetic field lines cut the conductor, the rate at which the magnetic field lines cut the conductor is directly proportional to the EMF or current being produced. EMF means voltage, electromotive force. So the rate of cutting of the magnetic field is proportional to the EMF or current being produced. Right? So the faster, larger. So if I increase this, I'll increase this. If I decrease, same thing, right? Right? Everybody remember what directly means? Right? Directly means if you increase one, they will also increase the other. Okay? Are you okay with that? Yeah? So that was Faraday. So Faraday said, Vishish, you can explain what Faraday said here? Why I keep going, right? Because you're not paying attention.
So,
Right, so what you say? Sorry, what do I know?
but the next class.
Huh?
But the next class.
Right, watch here. So, right, Helena, watching here. So watch this here, right? So the faster I take this, remember around here have magnetic fields, right? The faster I take this and I move it in and out, the bigger the current reading here. All right? But what is a galvanometer? Anybody knows? What's the difference between a galvanometer and an ammeter? Galvanometers will only tell you the current that's there. The ammeter will give you an actual value like 12 or 19. The galvanometer will just tell you current positive or current negative. It doesn't give you a value. Okay? So for example, when the magnet moves in, the galvanometer will tell you, okay, current positive. When it's moving out, it will show you something else. Huh? So the galvanometer shows the direction of current. Right? So watch this here. What would happen if the galvanometer deflects quite down here? Does that show a bigger current or a smaller current? Right. So the lower it goes, the bigger the current. Are you okay with that? So one direction will be positive, one is negative. Okay? So a large deflection, small deflection. Right? Large deflection, small deflection. Right, Kanisha? So the faster I move this magnet in and out of here, bigger this is. Right, Kanisha? Suppose I move it real slow, Kanisha. Will you get a big deflection? No. Suppose I just bring it real close but stop right here. Would you get a deflection? Probably not. Right? Probably not. Suppose I wanted to increase the deflection. What can I do? Suppose I wanted it to be real big. What can I do? Huh? More what? Right, move it faster. And one more thing. A stronger magnet. Right? And something else that you all may not know as yet. More coils. Right? More coils, stronger magnet, move faster. Those three things can help increase current being induced. Actually, you know what? That's something good for you to have. Megan only laughing now. Now why? Right. What were the three things again? They pick on like pick on who? Megan, the one that was laughing. Megan, number one.
Bigger magnet.
Larger magnet. So I'll use the word stronger magnet, right? Number two, next Soraya, what's the name again? Justin. More coils. More coils here, right? And the last one, let's take somebody online. Let me see who most likely not listening here. Pickle? Joshua, now, let us pick who? Rajiv Narayan Singh. Rajiv. I need some help, Rajiv. What's the last thing that would help increase the current here being induced? We said more, Justin said more coils and Megan said stronger magnets.
Oh.
Rajiv. Rajiv said the speed. All right, I'll take that. Right, speed of moving the magnet, right? Moving the magnet. Sorry.
That's it.
Right, now for the hard law. Last thing we do it. Take a 1 minute, bring out there, right, nice. Yeah, go ahead. All right, now,
That's you. Alright, that's what's good for
right, let's go. Last one, lenses law.
So we still.
What, everything's still there? Lenses law. Alright, ready? Right, last one. Lenses law. Lenses law, we go right here. Lenses law allows us to figure out the direction of current here. Right? Faraday gives us the strength of the current. Lens gives us the direction. All right, so make a note of that, right? Lens will give you the direction of the current, and Faraday gives you the strength of the current. Magnitude. Up next, you can remember, I want to start a little bit earlier. You get some more time. 1 o'clock, 2 o'clock. We'll just plug in, we can pass. Huh? Oh, okay. Alright, ready? Right, sorry. Right, so here, lens now is going to help us figure out the direction of the induced current. Right? So take the small ruler. Lenz's law states that. Lenz's law states that. So you have to revise it more summary of everything. Okay. Lenz's law states that the direction of the induced EMF, guess here again, true. The direction of the induced EMF / current, the direction of the induced EMF, right, / current, always opposes motion. Always opposes the motion.
Always.
Always opposes the motion. In this case, of the magnet. But it always opposes motion. Catch the idea, sir? All right, so everybody pay attention here. This is probably the hardest thing from today. All right. Right. So here's what Len said. Len said that the direction of the current here always opposes motion. So my question to you is, ready? The way to be lost, right? You can always get the notes. So always opposes motion means what? If I am moving this way, what does opposed motion mean? I want to send you out, right? So if here is north, what will send it out? What pole will push it out? A north. And a north pole will push the magnet outwards. Correct? And if here is north, here is what? And if we know the direction of the north, because we use the right-hand grip rule and figure out current direction. So watch it here. Ready? Right? So here's where you have to envision it, right? So north is here, north is towards me, south is there. So my fingers, right hand, grip rule, my fingers are going into the whiteboard and then coming out. So you're going in at the top, in, and then coming back out. So watch this here. Watch it closely here. In at the top, out here. In, out. In, out. So it means that current going this way. You'll see that? And if current going this way, the needle points in the same direction. That's okay? So the galvanometer needle will go to the left. That's all right? Everybody okay with that? Watch it again. The magnet moving inwards. So if here's a north, to oppose the north, I have to create a north here. Right? Well, not me, right? Technically, that's how God make it, right? So a north will be created here to push it outwards. So if here is north and here is south, we use the right-hand grip rule, right? Thumb points towards the north and the fingers point in the direction of the current. So the current going in at the top, coming out at the bottom, and it will follow something like that. That's okay? So in exam, you have to pay attention to how the coil moving. Right, Aria? And the current moves in the direction as the galvanometer. Yeah? You see that? So, what do you think will happen to theta when it's moving outwards? Here becomes what? South. Why? Because they want it to come back in. Here is south and here is. So therefore the current will move out. Other way. That's okay? Once you figure out one, you can figure out the next one. Everybody okay with that? Right? So that's the reason why every time the magnet on the simulation, remember it, every time you get a north, it's going one way, and then when the south reach in, went the next way, right? That's the reason why. Every time the direction or the magnetic field direction changes, current direction also changes. Okay? So when the north moving in, it going to the left. When the north moving out, it goes to the right. That's okay? So you have to be able to work it out regardless of what pole they give you here. The next option, the south and south. Right? If it's a south here, it might behave like this. If it's a south coming out, it might behave like this. Right? Just the reverse. You okay with that? Yeah? Are you okay with that? Copy that down. And copy that down. That's all I'm doing. I don't see the arrow. Right, so to the negative here, positive here. That is your lenses law. Next day, we'll go to the generator. And then we have transformers that bring to the map. Right, and then we. Yeah. Next video. Right? I just want to give you two small notes to write next to it, right? Right, just two small notes. Note that for this one.
There's no what?
Perfect.
Wow.
Right, so north pole moving in, and north is induced closest to the magnet. And here, north moving out. So this right?
Yes. Wait, no, you started.
Yes. Right? Why did this? Oh, just one question before we go. Anybody can answer. Anybody can answer. Why do you think how to ask it? Why do you think this happens? Why do you think it producing a pole to oppose motion as opposed to go with the motion? Why do you think it making you oppose the motion? Why you think so? Because the next thing you just pull the magnet in, right? But why oppose the motion? It has to do with the conservation of energy. Right? Remember, mechanical is being converted into what? Electrical. So the more mechanical you have, the more electrical you will have. So do you have to push harder or easier when you're posing? Harder. So the more mechanical, the more electrical. Right? Remember, this is not 100% efficient, right? Everybody okay with that? So the reason is more mechanical will give you more electrical. All right? All right, so nice. That brings us to the end of that. Well, our mandatory group speaker start earlier next week, right? Or we'll just do that. I'll do nothing. Don't think I might learn something. Everything will be tiny here, I'll do. All right, nice.